All right, welcome back. In this, we're going to go over intro to alkynes, acidity, and preparation. I made a lifetime total of $508.06. All right, we finally made it to alkynes. So let's talk about what we're gonna go over in this video. I'm going to assume that 2/3 of this video you probably don't care for as much as you would like to. You care about the preparation part of this video, but that does not mean you won't be tested on the other 2/3, because I was, and you should be prepared for it. Now we're going to talk about what alkynes are. Then we're going to talk about naming alkynes. Then we're going to talk about acidity and pKa of terminal alkynes. This is very important, and this actually builds off onto preparation of alkynes. Then we're going to talk about the recipe on how to do the reaction, and then we're going to do the mechanism and practice problem and mechanism. Okay. Alkynes is the next functional group that we're going to go over. They are triple bonded carbon-carbon atoms. There are two main types of alkynes. There's terminal alkynes, where we have one R group, so this carbons is an R group. Our alkyne is right here. We have one R group, and then we have one hydrogen. That's a terminal alkyne. Internal alkynes have no hydrogens. They're just both R groups here. This will play a role a bit later. Okay, a very common question I have is, when do we see alkynes? And I guarantee you, if you are female, you probably may have encountered them already. If you are in a loving relationship, or maybe not a loving relationship, you're just having fun, you have consumed alkynes. And people do this to prevent what will happen in 9 months. What I'm talking about is birth control. Birth control is made up of alkynes. Now, you don't necessarily have to be in a sexual relationship to be on birth control. Women take birth control to control periods if they're pretty bad, because birth control is a combination, or can be a combination, of estrogen or estradiol and progesterone, P4. Now, depending on what's going on in your body, it's an imbalance between those hormones. So that's why you take birth control, to control it, and that's how periods happen. Or periods don't happen if you control it, I should say. Okay, whatever. Oh boy. That's a very interesting example, I know. But, okay. Alkynes have the suffix "-ine" at the end. It's very important when you name alkynes, when you number the parent chain, that the alkyne, the triple bond, must be on the lowest numbered carbon possible. As you can see, we have 7 carbons in the parent chain here. Number 2 and number 3 belong to the alkyne, because we need to get it as low as possible. Now remember, when naming molecules, numbers are separated by commas from other numbers, and hyphens separate numbers and letters. So you're going to number the parent chain, make sure the alkyne is lowest, and then figure out the substituents that branch off of the parent chain. So for here, carbon 5 has 2 methyl groups, and carbon 6 has 1 methyl group. We can combine the methyls together to call it trimethyl. So you can call it 5, 5, 6 hyphen trimethyl hyphen, and now you need to signify where the alkyne is located. You are going to put the number where the alkyne starts. Even though the alkyne is part of both carbon 2 and carbon 3, you put the lowest number in the name. So it's going to be hyphen 2 hyphen heptine. And that's how you do it. Or you can do it this way, name it that way. I personally don't like it. I like the top way better because it's just easier. And that's really it. That's what naming alkynes is. Okay. Acidity and pKa of terminal alkynes. Terminal alkynes tend to be more acidic than alkenes and alkanes. This means they want to give up a proton, or they want to be deprotonated, in other words. Now, why are we talking about terminal alkynes, not internal alkynes? Why does this only matter for terminal? Well, acidity is giving up a proton. Well, internal alkynes don't have any protons to give from the alkyne. They don't exist. They're only R groups here. This is carbons. Terminal has 1 hydrogen that can give up, so that's why it's acidic. Yeah, we're here. Okay. Now, remember, lower pKa values mean stronger the acid. In other words, lower pKa means it wants to be deprotonated. It wants to give up the proton. Now, pKa is given through usually a pKa chart. So on an exam, you'll be given a pKa chart, or you'll be stated the pKa values on the actual exam. So don't stress about it if you see pKa values and you're like, oh, did I get this? It's from a chart. Okay, acid-base reactions are equilibrium reactions. Now, they always favor weak acid and weak bases. So the equilibrium always lies in the direction of the weak acid and the weak base. So let me show you an example. Say we have a base and we have an acid. You'll notice it's a stronger acid and stronger base. The stronger is comparing from the reactants to the products. So I'm comparing this side to this side. This base is stronger than this side. That's what I'm trying to say. Okay, so the stronger base, or the strong base, the conjugate becomes the weaker acid. That's just by definition. And then the strong acid, the conjugate is a weaker base. Okay, you probably don't care about this too much. Or you probably do. Okay. What I'm trying to get at is when the stronger base deprotonates the stronger acid. So what's happening is the base is stealing the proton for itself, and then it becomes the acid, because now it has protons, an extra proton. So the stronger acid is being deprotonated, so it's being left without a proton, so and therefore it's a base. When this happens, the weaker side, whatever pKa value of the acid, if it's higher than the reactants, what you started off with, the equilibrium is going to favor this side. In other words, the deprotonation is favored. It will happen. This is like saying the base is strong enough to deprotonate the alkyne. And this happens when the acid is stronger when getting deprotonated. Okay, hopefully that makes sense. Let me show you the other example the other way. Say if you have a weaker base and a weaker acid. Remember, these weaker terms are comparing the reactants to the product side. You'll notice that the product side here has a lower pKa than this. So that is by definition, since lower pKa values mean it's a stronger acid, that is why I'm saying this is a stronger acid than this. And this is coming from the pKa chart. I'm saying that pKa is 15.7 from the pKa chart that I did not put here, but you'll see it. It's in every textbook. Okay, in this scenario, the weaker base is attacking the weaker acid and tries to deprotonate it. It's trying to deprotonate the weaker acid. So the stronger acid now is deprotonated. Yeah, protonated, sorry. So this has now been protonated to the stronger acid, and now the stronger base has been deprotonated. So this was the weaker acid, is now been deprotonated to become the stronger base. Now you're probably like, okay, why do I care about this? You'll see that the equilibrium, the top here favoring the left, is bigger than the right. What this is saying is deprotonation is not going to happen. It is not favored. That, in other words, means a weaker base is not strong enough to deprotonate an alkyne. So moral of the story is only strong bases can deprotonate terminal alkynes, and this is going to play a role in the very next slide. So if you were asked, compare the pKa values from the table that you're going to be given and determine if deprotonation will be successful. That's what we're going to do. All right. Preparation of alkynes. Alkynes can be made from alkyl dihalides. So you need an alkane with 2 halides on it to turn it into an alkyne. So what's going to happen is the first time you use a base, it's going to create an alkene. And then the second time you use a base, it's going to create an alkyne. Alkene and an alkyne. Now the mechanism is the same if your alkyl dihalide is geminal or vicinal. What geminal means is the 2 halides on the alkane are on the same carbon. You'll see that this carbon is bonded to 2 halogens. This is geminal. If the if this carbon had only one halogen and then this carbon had the other halogen, that would be vicinal. The mechanism is the exact same thing. Everything's happening the exact same thing. It's just two different types. Okay, here's the recipe. The first round of elimination can use a variety of bases. It really does not matter. So what I'm saying is this round right here can really use any base. It's the second round that's the problem. The second round, it needs to use a very, very strong base. Otherwise, it won't happen. So after the second round, we get our alkyne. So we have finished. We have got our alkyne. Now, if we do a third round, we would get an alkanide ion. This can be undone by adding water. So you're probably like, I don't get this. You will see when we do the mechanism what I'm talking about. Now, it is very hard to control how much base you put in the reactant, in the beaker. That's what I'm trying to say. That's why I put this last part here. So what we do is rewrite it as excess sodium amide in liquid ammonia. So we have our alkane here with 2 bromines. This is geminal because the carbon has 2 halogens attached to it. One carbon has 2 halogens attached to it, so it's geminal. It can work for vicinal too, but this is geminal. What we're saying is we're putting excess sodium amide in liquid ammonia, and then we're doing we're adding water at the end. This creates our terminal alkyne. Now, the reason we're saying excess here is because it is very hard to control putting 2 equivalents of base in a beaker. It's very hard to control. In other words, it's very hard to stop here. Because when you put, bases in a beaker, you're just putting a lot, right? You can't control how much you're really going to put. And you can't stop it. So that's why we just put a lot of it, and then we fix it by adding water. And you'll see exactly what I mean right now. Okay, tell me the product of the following reaction by drawing the mechanism. Okay, so we have a geminal alkane, dihalide, and we're treating with excess this crap, okay, with water. So what do we do? What's the product? How do you do the mechanism? The first step is we are got to do an elimination reaction. Does not matter which halogen you start with. This is the alpha carbon, this is the beta carbon, this is the beta carbon. Notice that this beta carbon has no hydrogens to sacrifice. This one has 3. So that's where we're going to use. We're going to use any of these 3 hydrogens branching off of here. Okay. NH2. We're going to use it. It's going to steal the proton. This bond dissociates and becomes over there, forming an alkene, and then this kicks off our leaving group. This is a basic elimination reaction like we've been doing forever, since time began. Now you're probably wondering, what is this sodium part and this part? Sodium part. Sodium does nothing. This is just to balance the ion. Because remember, in all bases and when you do SN2 reactions and E2 reactions, I always said that sodium, the ion itself, like potassium or sodium, doesn't do anything. It's just there. It's just to trick you. It's just there to balance the molecule out, so it's not stable. It's stable. So we only care about this. That's everything that's doing the reaction is this. Okay, we do that. We get our alkene. Then we have to do it again to get rid of the other halogen. Okay, so this is the alpha carbon, this is the beta carbon, this is the beta carbon. No hydrogens here, so we have to get rid of the hydrogen here or here. We can choose either or. So we're going to do that. We're going to take this one. Okay, we take that. We have now formed an alkyne, and we kick off the leaving group. Goodbye. We have our alkyne now. Now we have excess of this crap here. So we have to keep doing it. We have to keep going. So it's going to deprotonate it again. We cannot stop. That's just the unfortunate part of this reaction. So this goes, and then now the electrons go there on that carbon, forming an anion. So what do we do? What do we do to fix this? We have an anion now. Well, we use water. Water, we're going to do a proton transfer. The electrons are going to attack the water, protonating this. So the charge is no longer there. We no longer have the charge there. We don't have the ion there. So now we're left with a terminal alkyne, and then we are left with hydroxide. So I should actually say plus OH. There. Okay. Let's do this one. Oh yeah, that's the answer, by the way. This is the answer. Okay. Oh boy. Okay, so we do not have a geminal alkane. We have vicinal. So what do we do? Same thing. Same process. Same, we can choose which halide to start off with. Does not matter. This is the alpha carbon. This is the beta carbon. We have nothing here that we can produce. No hydrogens that we can sacrifice. This is the beta carbon. So there is a hydrogen there. There's 2 hydrogens there. Now, if we start with this one, this is the alpha carbon, this is the beta carbon. We have 1 hydrogen we can use. So it does not matter what you want to do. So we're going to steal this one. So we're going to kick off this hydrogen first, this halogen first. So we do that. Now we are left with an alkene. Like that. So we have to do it again. We have to get rid of that halogen and get that alkyne formation. Okay, this is the alpha carbon, this is the beta carbon. We do not take this one because it's part of the alpha carbon. We have to take this one. This is the beta carbon. We steal the beta hydrogen. Okay, so let's do that. We form the alkyne. Kick off the halogen. We are left with this. Same thing. Now we have to keep going because we cannot control how much base we have in our beaker. We just put a lot of it. We put a shit ton of it. So we deprotonate again. And then we do this to get the anion. And then we do the same thing, water. And yeah, and then we're left with hydroxide. Yay! Okay, that's their answer. So it's literally the same answer. See that? Okay, that's it. If you found this video helpful, please like and subscribe. Until next time, later.